In this video, we are going to discuss hydrogen bonds, which are a particularly strong form of intermolecular force. Our learning goals are to understand why they are stronger than our regular dipole-dipole forces and where they come from. I want to start by proposing a little bit of a puzzle. I'm showing oxalic acid here, and a couple of facts about oxalic acid is it has no dipole moment. So this is very much like the difluoro and dichloroethylene compounds we looked at in an earlier video. But at the same time, it is a solid at room temperature, which suggests that it has very strong intermolecular forces. So why is it a solid? What is giving it this extra adhesive power with itself that allows it to remain a solid even at room temperature? Well, to understand this, we're going to need to probe a little bit deeper into the dipole-dipole interaction. And I want you to imagine that there are two molecules that have partial charges. And one of those, the negative charge, is associated with a piece of the molecule that has an extra pair of non-bonding electrons. Now, those two charge centers are going to experience an electrostatic attraction, okay, with an electrophile on the left side and a nucleophile on the right side. The attractions between these partial charges will partially offset the electron-electron repulsions that come from the electron clouds on each of these parts of the molecule. When these molecules come to closest approach, though, we'll reach a point where those electrostatic repulsions between the electrons on either molecule are strong enough to oppose the attractive force between those partial charges. So there will come to be a separation distance that is the preferred separation for these two molecules in their dipole-dipole interaction. And that could be quite a long distance, comparatively speaking. The molecules are still going to be next to one another, but it does limit how strongly they can interact, because remember, the strength of that dipole by dipole, or the partial charge force, is dependent upon the separation, and the larger the separation, the weaker that force. Let's see how this changes now, though, when we have a partial charge that's associated with a hydrogen atom. So we're going to suppose that hydrogen on a molecule is bonded to a very electronegative atom, particularly nitrogen and oxygen, although it can also include fluorine. In this case, we have, and this is a case for an alcohol, we'd have hydrogen bonded to an oxygen, which is then bonded to the rest of the molecule, and it creates a strong bond dipole with a partial positive charge on hydrogen, a partial negative charge on oxygen. Hydrogen doesn't have any core electrons, so it can actually approach closer to a different molecule of the same type and get closer to that nucleophile on the other molecule. So when we bring it to equilibrium separation, it's a much closer separation, and the interaction is going to be stronger at these small distances. Now, I'll note that because we're attaching hydrogen to a very electronegative element, the partial charges are going to be larger in this case, and they can now approach each other closer. So the net effect is to make a very strong dipole-dipole interaction, and because it's particular to having hydrogen involved, we call this a hydrogen bond. You shouldn't confuse this with a covalent bond to hydrogen. It is a particular type of dipole-dipole interaction that is enhanced by involving a hydrogen. So let's examine what relative hydrogen bond strengths can be. Remember that hydrogen bonds can occur only when hydrogen is bonded to nitrogen or oxygen. So the nucleophile between two molecules that have this will be the nitrogen atom or the oxygen atom. They are also where the partial negative charge is going to exist. Now, we need to have three atoms to be collinear to make this happen. Okay, two of those atoms are the nucleophile atoms, one on one molecule and one on the other that's attached to the hydrogen that's creating this special hydrogen bond. Those three atoms must be collinear. I want to note that the electronegativity of oxygen is greater than that of nitrogen, so there's a greater charge separation, and therefore hydrogen is a better electrophile when it is attached to oxygen than when it's attached to nitrogen. They're both pretty good, but oxygen's a little bit better at donating hydrogen to this hydrogen bond. Nitrogen, however, is a better nucleophile, and it can donate its electrons easier, so it's going to be better as the acceptor of this hydrogen bond. So let's create a table to show this. All right, what I'm showing here is the donor side, which is the side that provides the hydrogen as part of this hydrogen bond. And the acceptor side is the nucleophile that the hydrogen interacts with to create the hydrogen bond. So the best possible combination is when hydrogen is covalently bonded to oxygen, which draws its electrons away, so it becomes a better donor for the hydrogen bond. And the nucleophile is nitrogen. In that case, the strength of this hydrogen bond is about 30 kilojoules per mole. The next best one is where oxygen is the nucleophile for the same donor hydrogen, and that strength is about 20 kilojoules per mole. The weakest combination is when the hydrogen is attached covalently to a nitrogen, so it doesn't have as strong a charge separation, and the nucleophile is an oxygen. That is the weakest type of hydrogen bond, which is still 8 kilojoules per mole. Should note that the hydrogen bonds in this case are all about 1/15 the strength of covalent bonds, so they are a weaker interaction than a real chemical bonding interaction. Nevertheless, they're somewhat stronger than other intermolecular interactions that we can devise. So, does this provide us with a resolution for oxalic acid? Well, let's look at carboxylic acids. Now, they feature acidic hydrogens. These are all bonded to oxygen, so those are the electrophiles. It also has an electron-rich nucleophile on the carbonyl bond. So that's a different part of the same molecule, but that's what forms the nucleophile in this hydrogen bond. So the result is that we're going to generate hydrogen-bonded carboxylic acid dimers that look something like this. Here are the two carboxylic acid molecules that are going to form hydrogen bonds. They form these hydrogen bonds between the hydrogen on one and the carbonyl oxygen on the other in both cases. And they have these charge separations, and because they can get close to generate these very strong hydrogen bonds, and they have two of them, this means that the intermolecular forces between carboxylic acid molecules are much stronger, and it leads to higher phase change temperatures for carboxylic acids. So now when we look at the oxalic acid structure, it actually is a large network of oxalic acid molecules, each of which can participate in a total of 4 different hydrogen bonds, 2 of them through its hydrogen atoms and 2 of them through its carbonyl oxygens, because it's a dicarboxylic acid. So this is really the reason why oxalic acid forms a solid at room temperature, because it has this great framework of very strong intermolecular forces through its hydrogen bonds. Now let's look at another indication of the strength of hydrogen bonds, and I want to consider the boiling points of compounds between elements in the main group of the periodic table and hydrogen. So I'm showing you 4 of these, and I'll show you where they are in the periodic table. It's these 4 groups that are forming bonds to hydrogen. So in the case of the carbon group, it would be like methane, silane, germane, and stannane. In the case of the nitrogen group, it would be ammonia and phosphorus hydride and arsenic hydride and so forth. And you can see that these boiling points all get larger as we go down these groups. Okay, I'm only showing you the 2nd, 3rd, and 4th members of these groups for a reason, which you'll see presently. But this is an expected behavior because as we go down those groups, the atoms that are attached to hydrogen are larger and larger, so they have stronger dispersion forces. This is a natural effect that we typically see in lots of these different things. The surprising effect of all of this, though, is what happens when we go to the top member of these groups. Where are the boiling points for the fundamental compounds that involve carbon, nitrogen, oxygen, and fluorine? Well, you can see the carbon case, methane, is sort of following the same trend. It has the lowest boiling point of all of the elements in this group. It is the lightest element. But ammonia, hydrogen fluoride, and water are all dramatically out of place when it comes to this trend. Those boiling points are much higher, suggesting that those molecules have very strong intermolecular interactions. And the cause of those intermolecular interactions in each of those cases is hydrogen bonding. So here we can see a very dramatic effect of hydrogen bonding because it causes anomalously high boiling points for these very light molecules because they have these strong intermolecular forces. Now the case is even better for water. Okay, and water is a very special instance of hydrogen bonding, and it's why its boiling point is so extraordinarily high. It forms strong hydrogen bonds, but it's the number of hydrogen bonds that it can form that really makes it optimal. Okay, here is a picture of a water molecule in the middle, and it's actually forming hydrogen bonds to 4 different water molecules. Basically, both of the electron pairs on its oxygen can form hydrogen bonds, and both of the hydrogens that the oxygen is attached to can form hydrogen bonds. This is like the best you can do. This is the optimal setting. So because of this, oxygen can form this large network of hydrogen bonded water-water interactions, and that's what leads water to a very high boiling point. It leads to very strong intermolecular forces, and these mean that it has higher boiling temperature, it has very strong cohesive and adhesive forces, and relatively high surface tension. Okay, all of these are very peculiar to water. It's not the only molecule in the world that has strong cohesive forces, but because it is so light and so plentiful, it gives it very special properties that make it truly extraordinary in our universe. So you can appreciate something about water that perhaps you didn't know before.